Hi, everyone. My name is Jonathan Gordon, and today I'm going to discuss the trie data structure, which is also known as the prefix tree. So, have you ever wondered why Google's so fast when you type in the letters PY and immediately get back words like Python and PyTorch? Well, it's probably based on a data structure called the trie. But first, let's talk about the trie history. In 1959, René de la Briandice abstractly described the trie. It's derived from the word retrieval, but we pronounce it like try because we don't want to confuse it with other trees such as the binary tree or the search tree. The term trie was first coined by Edward Fredkin in 1960. So let's look at a trie. So I want you to look at the middle branch starting with the letter Q. Notice for all three words, we walk the same path. Q, U, I, T for quit, E for quiet, and QUIZ for quiz. Now notice that they all share the same prefix, QUI. What's really neat about this is that we don't waste any space for the prefix, even for completed words like quit and quiet. Now, we can also look at another list of words like a, alone, and part. So notice that a is shared prefix for both alone, ALONE, and apart, APART. So that is the power of using a trie. It allows us to get direct access to words just by traversing the node starting with the prefix. So, how would we delete a word from this trie? So, let's say we wanted to delete the word zoo, ZOO. So, what we would do is we'd start at the O, we'd remove this node, then we'd remove this node. But when we get to Z, we can't remove that node because it is a parent of zebra, ZEBRA. But if we wanted to remove zebra as well, then we would do the same steps. We'd remove the A, the R, the B, the E, and when we got to the Z, we would notice that no other um, words use this prefix, so then we could safely delete the Z as well. So let's talk about why a trie is so powerful. One of the main use cases for trie is the autocomplete. So for example, let's say we were in our Google search bar and we typed in QUI. Well, immediately, because we followed this path, we would be offered quiet and quiz and also quit. So that is the power of trie. No matter how large this data structure is, in order to find quit, quiet, and quiz, we just traverse this one node path that branches right here at the eye. And that is the power of trie. Let's take a look at the code. Let's start with the trie node. Notice in the initialization, we first create a dictionary of children. This is basically used to point to nodes that will form future prefixes and words. Now, to mark the end of a word, we have a flag called is end of the word, currently set to false. But if we reach a node, which is actually the end of the word, we will set this to true. This becomes really useful, especially for prefixes that are complete words that make up larger words. So let's now move on to the class trie. I'm not going to go over all the code, but I will have a link to all the code underneath this video. But just from a high level, we've got our initialization, we've got our insert, we've got our delete, we've got our autocomplete, we've got our search, and we've got our start with. Now, the one interesting thing is when we initialize this class, we start off with an empty trie node and we set our root to it. So most of these methods are relatively simple. For the insert, you can see it's not much code. But I will say the code for delete Gets a little tricky, mainly because you have to deal with prefixes that are actually complete words and you can't delete them because they're the prefix to larger words. Again, I'm not going to go deep into the code, but it's probably the most complicated part of the code base. So let's talk about the big O of the trie. So if you look at this table, you will notice a very specific pattern. Almost every operation is O of L. So what is L? L is the length of the word. So why aren't we using N? Well, because that's the total number of items in the data structure, which usually drives the speed, but it actually gets canceled out in the big O of a trie. So for insertion, prefix search, search, and delete, the time it takes is strictly proportional to L, the length of the word you're typing. It takes the exact same amount of time to find the word quit in the data structure of 10 words as it does in a data structure of 10 million. Obviously, the exception is autocomplete, which has a big O of L plus V, where V is the cost of collecting all the visiting neighbors like quiz and quiet. But the bottom line, the trie is scalable. You can double or triple your data set size and your core operations won't slow down by a single millisecond. Other data structures we could possibly store a list in to do some searching. We have the ordered linked list, which is simple. It's great for returning and iterating through a already ordered list. But for searching, for example, to find the word zebra, we have to go all the way to the very end to find zebra, which is super slow. Then we have our Python list, which is actually pretty fast. But the problem with the Python list is it's ordered by index. So in order to find the word quit, we actually have to go through all the different indexes, and then we have to look at the reference of the word it's pointing to finally analyze, hey, is this the word we're looking for, quit? It is, and then we return it. It's just a lot of work. And then finally, we have the Python set. Now for searching, this one's the king. Basically, we use math. We take the word, we compute its hash function or its hash value, and then we were able to find it immediately because we're able to look it up based on the hash math. For example, if we wanted to find quit, we'd run the math, we'd get to index 6, and we'd immediately find quit. So it's really fast for retrieval of exact matches. Not so much for autocomplete. Let's talk about insertion performance. This graph, we have about 800,000 words. The duration goes up to about 2.5 seconds. You can see that the trie was the slowest. The list and the set are almost hugging the bottom down here. The reason the trie is so slow is for each character, we have to create a node, a reference in that dictionary, and it just takes a lot of time. Let's talk about search performance, the exact match. Now, all that work we did building the trie, now it starts to pay off. Notice the list falls off the cliff. For 100,000 words, it takes 17 seconds. That's a lot. Now look at the set. It's hugging the bottom. That's because of the set's superpower. It's the king. Then we have the trie. It's in the middle. Still does pretty well. But why is it slower than the set? Well, it's because it has to walk the tree node by node for the length of the word. All that pointer chasing, it's more expensive than the set's simple hash calculation. Now let's talk about the trie advantage, the prefix search. Now, if you notice, the trie, the yellow line, is hugging the bottom. This is where the trie comes into play. Remember, I said it's O of L complexity? This is it in action. The trie does not care that there are 800,000 words in this data structure because it only has to look at 3 or 4 letters of the prefix. It ignores the rest of the data. And look at who the loser is. It's the set. Set is the wrong tool for a prefix search because it's built for exact matches. You have to iterate over everything to find out if it's a prefix or not. And same with the list. You still have that ON, big O, because you have to scan every word. Slightly faster than the set. But, in the end, the try, this is the winner. Well, one quick note I need to point out about the set. It's awfully slow because of the way I implemented it. I think if you were to create a set and hash every prefix, it actually may come down to be quite fast, maybe similar to the try, but I didn't do that implementation. So let's talk about the autocomplete performance. Notice that the try is a clear winner here. The list is actually pretty fast, most likely because it's using power short. And then we have the set, which is extremely slow. But again, it could be because of my implementation. I think if I would have created a hash, you know, for every prefix, it would have been really fast as well. So the takeaway here is the list and the set are fast if you check everything, but the try is the only one that knows how to skip data. It doesn't check 800,000 words, it only checks the ones that matter. So finally, I want to go over a little console app I said I'd create. Create a little helper, load words from file generator. And here's my search app. And basically what it does is it loads this Google 1000 English text that I'll put a source for. And let's see if I can make a little search engine. So here we go. Let's type in Python. Let's see. Oh, I found Python. How about well, there you go. There's my little search app. Seems to work. Let's quit out of here. Thanks, everyone. It's been really nice presenting to you.